Okay, today's question is 973, k closest the points to origin. We are given a list of points on the plane, and we need to find the k closest points to the origin. So the point here is represented as two numbers, as the location on the 2D space. So in order to figure out which point is closer to the origin than some other points, is to have a definition of distance. The distance here in this question is the Euclidean distance, which is the square root of the sum of the squares. As the example here, we have 1, 3, minus 2, and 2. So the distance between the first point and the origin is sum of the squares. 1 plus 9 is 10, and square root is 10. The distance is square root of 10. For the second point, it's minus 2 minus 0 minus 2, square that, 0 minus 2, square of that, and summing those two numbers, which is 4 plus 4 is 8, and then we take square root. If we're asking the closest one, k with k equal 1, we return the point with a smaller distance. That's the answer to this question. So the most straightforward way of solving this problem is to just sort the whole list using the distance method, right? And return the first k points from the sorted list. So if we use some kind of in-place sort, the space complexity will be constant, and the time complexity is n log n, with n be the number of points. If we do that, then there may be this thing pop up, that they may say that we don't care about the order of this k things. You can return it in any order. Is there any better way that you can solve this problem? So this hint will give us an idea that we are doing some extra work by sorting the whole thing, right? Which is not needed. If we sort the list of points and take the first k is in sorted order. If we don't care about that, then there are other ways of doing that. One way to it's fairly easy to code up is to using a priority queue. So the idea is to look at the points one at a time, right, and try to push the points onto a priority queue of size k, and the elements on the priority queue is the k closest points to the origin that we have seen so far during this whole process. And at any given point, we find a new point. We are looking at a new point. We try to compare that point with the zeroth element on the priority queue, the gatekeeper or top element, and try to determine whether we need to do something to the priority queue. Popping the first one and maybe putting the new point onto the priority queue and heapify the priority queue again. So in that case, the gatekeeper on the priority queue must be the maximum element of this k closest one, k smallest one. So in that sense, we should be using a maximum queue. In terms of space and time complexity, because we're maintaining a priority queue of size k, we have order of k time space complexity there. But for the time complexity, because any operation around inserting or deleting elements from heapify the priority of queue of size k, it's log of k. So we have n points, then the total time complexity is n log k. And in the end, we just return the top k elements. We just return the elements from the priority queue. And as a result, the return answer is not necessarily in sorted order. So that would be a solution to this question. So let's quickly code this up. Okay. So we'll have a priority queue, and let's define some helper function to calculate the distance of any points to the origin. So it's the sum of the squares, and take square root of that. And actually, we don't have to do this square root because the square root function is a monotonic function, right? So if 10 is bigger than 8, the square root of 10 is definitely going to be bigger than square root of 8. So with that, we can actually save some time by not actually computing the square root. So that's the that would be our distance function. So we are iterating over the points. P-O-I-N-T-S. We calculate the distance, and then if the priority queue is have less than k elements points, we definitely gonna put the new point onto it. Push, because we're using heap queue from Python is on min queue, min priority queue only, so we have to negate the value to make it to use it as a maximum queue. What we put on that is a tuple, which is the negative value of the distance and the point itself. If the priority queue already have the current k smaller closest value, the thing we need to do is to determine whether we have an even closer point. So we take the gatekeeper from the priority queue, and because the PQ0 is going to give us the gatekeeper, no, the tuple of the distance and the point, right? So the first element is the negative value of the distance, so we should negative that to get to the actual distance of the current farthest farthest point from origin in the current priority queue. And if that's the case, we should pop this point, pop this gatekeeper, and try to put the D on that. So there is this replace one. That's a combination of pop and push, which is it's slightly faster than if you do pop and push separately. So that's sorry, I forgot to put this here. So that's the pretty much the code for this priority queue solution. In the end, we just return try to get the actual point for element in the let's call it tuple, right? T in PQ. So that would be the solution using priority queue. Let me quickly go through this and see if we have any answers, any problems. So here we're passing a tuple of two things, and the distance is determined by the sum of the squares. Here we calculated the distance. If the priority queue has less than k elements, we would definitely want to push it onto that. And if it already has k elements, we do a quick check whether this point is closer to the origin than the gatekeeper. If that's the case, we pop the gatekeeper and push the new points onto it. And in the end, we just we return the points, not distance. So this seems okay to me. Let's try to submit it. Okay, it's working. It's about median in time, and we definitely use a lot more memory, but I'm not sure. It seems to be order of k. Okay, so this is the priority queue solution. Sometimes I guess this problem has also another even on average faster method solution, which is the Quickselect. It's a solution that's using the partition operation from Quicksort. So just in a nutshell, what the partition operation is doing, it's randomly picking a number element from the array and try to put the elements that are smaller than that onto the left of it, and try to put elements that's bigger than the pivot number you selected to the right of it. So after that operation, the selected element will be in its rightful location, in its final location on the sorted list. We are guaranteed to have elements prior to it to be smaller and elements bigger than it to be to the right, and the order of things between that and after that, it's not guaranteed. We only guarantee that all the elements that are smaller than it is being swapped to the left, and all the elements that are bigger than it is swapped to the right hand side of it. If it just so happened that the point is at the location k, then we are guaranteed that if we return the first k elements from this array at this point, it will satisfy our requirements. So in terms of time and space, the time is constant if we just do in-place swaps, right? And the time complexity is constant on average. But in the worst case, it's let's say that in the worst case, because the partition is order of n, and because we put we select an element and just have two pointers, one from the left and one from the right, and try to swap things, and the pointers meet in the middle. We do one pass to perform one partition, and then based on the location of this random selected pivot element, we then we only need to look at the left half or the right half. So we essentially reducing the space to half in average, right? And so in terms of amount of work, on the average we will have n operations in the first partition, then n over 2 in the second partition, n over 4 in the third partition, n over 8 in the next partition operation. So that the total is m plus n over 2 plus n over 4 plus n over 8, and so on and so forth. The summation of that whole thing sequence is 2n. So on average the time complexity is order of n. But in the worst case, we're not reducing the problem into half and half and half in each iteration. If we just reduce that by 1, then we have n, n-1, n-2, n-3, and so on and so forth. If that's the case, the time complexity will be n squared. So I guess if you don't know the selection sort, you will have problem understand what I was talking about. I might do a video about basic sorting algorithms, and if I ever done that, I will make an edit and put a link somewhere. So that's the method of solving this problem in constant time, on average. So let's code that solution up as well. Okay. So to do that, let's say that we have a method of sorting. We have 2 pointers, left and right, and k. What we need to do is to sort the whole thing initially with the 2 pointer at the 2 ends of this list. Points -1, and the k be the big K that's as input, and in the end we return the first k points. So then we have to do this what's in here. Here what we would do is to pick a random pivoting number, right? And we try to perform this partition operation, which we will implement very quickly after this. Partition left and right, and we can figure out so this M would be the location of the randomly selected pivot number in this whole point array after we done this partition operation. So the distance from this node and the location of this particular node node and point, and the left pointer is this distance, right? So if this distance is just so happen to be the k that we are currently looking at, we are pretty much done. Otherwise, if d is less than k, meaning that we haven't really find enough smaller points yet. We have some extra work to do, which is to the right hand side of it. So we have to do n+1 sort the thing from sorting, call this sorting from to the right of this number. The other case is that the other case is that after we do this partition, this particular element is to the right of the k location. Then we need to recursively do this method to the left. So that's with the left pointer unchanged. We change the right to n-1, and the k is still the k that we're looking at. So this recursive method here is the sorting routine. So then we have to define this partition operation with left and right pointers. We randomly select a location. We could use left +1. We could also use something in between, right? I guess using something in between may potentially have or we could use a random number. It doesn't really matter that much unless we have some kind of prior information, right? So we calculate the distance of this pivot number that we've chosen, and we will swap the left one with this pivot node. The swap is going to be an in-place swap. Swap ij points I. We swap the left end of the pivot element. So after that, we can try to have do a linear scan between our boundaries and try to put the smaller ones to the left and the bigger ones to the right. Left and right as a starting point. While these two pointers haven't met in the middle yet, we'll try to advance it and find the violations. And distance of points I is less than or equal to these pivot distance. We will increment I. So here we will have the same thing with the right pointer. We will be decrementing, and we're trying to look at if we have a larger distance. So these two while loops is to advance the points to a violation of the ordering. If I is less than j, meaning that I is still to the left and j is still to the right of this particular point, and we have the distance of point I is bigger than the distance of points j, then we need to swap I and j. And after this whole operation, we need to swap the left and the j again. So this index j is going to be the location of the pivot number, the pivot point that we selected in its. This j is going to be the final position of this pivot number that we selected, and then what we have left is this distance method, right? So here we have the points as a list of things, right? It's as a list of things. Okay, so x. Oh, if we have a function here, we could use that lambda, right? This thing, it's lambda x0. We use just using this thing. Okay, uncomment. Let's save the code if we have any problem. So the distance is just the sum of the squares. The swap is just in-place swap of two elements within the same list. The partition is we have a left pointer and right pointer. We try to randomly selecting some points in the middle of it and calculating the distance. We put that to the left, put the pivot elements to the left, and try to put the smaller things to the left and the bigger things to the right. And after that, we swap this this m element because we swapped with L, so in the end we swapped the L with J to put that back into its rightful location. So we just keep doing this until that we meet this criterion. So the middle minus L plus 1, the distance between the left pointer and this location of the partition is equal to the k that we want to look at. If it's greater than, if this distance is smaller than k, we perform recursively doing this on the right hand side, to the right hand side. If d is greater than k, then we're recursively doing this to the left, because the pivot number is to the right of this k, so we recursively doing this to the left. And this is the initialize. This so yeah, I think it's good. Let's submit it. Function object is not subscribable. Points I, points j, dist. Oh, okay. I have round brackets. Let me try to run this on one example. Yeah, it works. Let's see. Okay, it works. It's quite slow. I guess it might be the distance calculation that's taking some time. Let me try to improve this a little bit. Cache, because the I might have some redundant calculation of the distance here, so I will put this in, decorate this function. Then I have to use points. Okay. Return y. And if that's the case, I have to unpack this points here. Okay, let's see. Yeah, it's slightly faster. Just wondering what if I have this to be L plus 1. It's wrong. What could be the problem? Let me just use the left point as the partition element. Oh, it works, but it was slightly slower than the middle one, right? Not really. I guess it's just a random, some random things here. But anyway, that's this is the Quickselect solution. It's average, in theory, it's an average order of n in time and constants in space. Except that we have some cost stack here, which I think it's log n here on average, right? We have to have like a just thinking of this as a binary search to find the particular location k element. This, I think, if we on average, it's reducing the thing. Not on average. On good cases, we have reducing the search space by half. The cost stack, I think it's log n. Okay, let's do some pretty things. Sorted points. Key equal to lambda x0 plus x1 2, and let's do this. we're sorting this points by the distance, and then we take top k. How would this do? Yeah, this is fastest so far, even though in theory this is the slowest. It's just that all the things we code up in Python, and this sorted thing, sorting is coded in C, I guess. So we're doing a lot of things then, and still slower than just a one-liner. So yeah, this question really spends a lot of time. It's so that's it for today.